feel free to do that.
There we go. Yeah, go.
Great. Cool. So everyone, can you use your reactions in Zoom and give me a thumbs up just so that I know that you're back from your break so that we can see that that you're here? Okay, I see some thumbs up. This is great. Okay, cool. So welcome everyone. I'm excited to speak to you guys today. So my talk, as Adi said, my name is Melissa. I'm a software engineer, and so I want to talk to you something a little bit different than the previous two professors talked about. You know, they talked about a lot of theoretical concepts and, you know, kind of some of the cool ways that you can get involved in programming. I want to talk about software engineering in particular and what that means to me and why I think it's something that's totally awesome. And if you like building things and solving puzzles, you might like this as well. So good. Okay. So a little bit about me, because I think it's important to kind of the context here. And if you have any questions, it's good to know my background so that you can ask those effectively. So as Adi said, I'm a lecturer at the University of Washington, which is where I did my undergraduate degree. And I am not a doctor. I didn't get my PhD. I teach at the university because I like to teach, but not because I like to do research. So don't ask me about research. I have opinions about it, but it's just not my thing. So that is, I'm not a researcher. My first job out of college, was at Facebook, which you may have heard of. So I spent a lot of years there working with them. And my current company is called Snowflake, which, if you are not really in the software industry yet, I would suggest I just don't want to talk about what we do because it's really complicated. But it's another company that deals with lots of big data. But ultimately, kind of what I associate myself as is I am the kind of person who spends a lot of my day in front of a computer trying to solve puzzles. So that's kind of what we're going to talk about today. So when I was a kid, personally, you know, like things that I love to do, I love playing with Legos and Connects. I love jigsaw puzzles and Sudokus and crossword puzzles and all of those kinds of things. And when I was young, I didn't really think about computers as being involved in that process at all, right? You know, building things was something that you did physically, and solving puzzles was something that I did physically. And I'm sure a lot of children can relate to this as well. But taking that kind of passion for constructing something larger out of small pieces, that kind of translates into the real world in a lot of different industries. So engineering as a discipline across all of the different career paths and all of the different degrees is all about building things and solving puzzles in order to build those things. So kind of examples of that: electrical engineering involves, you know, taking wires and resistors and transistors and connecting them all together so that you can build something that actually sends electrical signals and triggers electronics in really cool ways. Mechanical engineers assemble physical motors and gears and, you know, levers and switches and into real things that then like build other real things in real life, which is pretty cool. And chemical engineers will combine different types of chemicals or different types of compounds and molecules and put them together in different combinations and different reagents to try to build some new type of chemical procedure or medication or something like this. So engineers build things, solve puzzles across all of these different disciplines. Software engineers, we like to say sometimes we're not really engineers, but I would argue that we are the things that we are combining and building just happen to be computers. We are using computers in order to build things and solve puzzles. And so that's what we're going to walk through today. Is we are going to walk through a couple examples of how you would use a computer to solve a real world problem. Okay. And we're going to do this together. I really do prefer interactive presentations. So could you all make sure to open the chat in your Zoom app here? And can you just send me a little message that says hi? You can send it to everyone. You can send it just to me if you're comfortable. with that, whatever works for you. I just want to see that everyone's able to interact, because every time you see this little chat application in the upper right corner of the screen, we are going to solicit your feedback to kind of build this application together. Great. I see everyone says hi. Sounds fantastic. Okay, so one thing that I missed in my discussion of my own background is that between Facebook and Snowflake, I worked at a company called Convoy. And Convoy is a startup, so it was a small company trying to solve a problem that had never been solved before. And ultimately, it is now no longer in business. So if you search for it, you might not find it because it has gone out of business, unfortunately. But I still want to talk about that business and kind of solving these types of problems in the context of this business. So Convoy was a company that was in the trucking business, which is one of the most all-American businesses in the country. And in particular, Convoy was a what's called a broker, and we'll talk a little bit more about what a broker is in a minute. But the people who founded Convoy kind of looked at the world and looked at the trucking business and were like, we see some problems here. So I want to talk about what those problems are and how Convoy was going to try to solve those problems. So here's the problem. You have lots of companies in the United States that are making goods, making things. So one example here might be Procter & Gamble. Maybe you've heard of them. You've got Kroger, you've got Walmart, you've got Costco, you've got, like any of the company, Hershey's, Anheuser-Busch, all of these companies are making goods, and they need to get their goods to the places where those goods are sold. So that might be a Family Dollar or a Safeway or a QFC or another Walmart where things are being sold. Okay, so that's the problem. People need to buy things, and the companies that make the things need to get the goods to those destinations. Okay, so let's say Procter & Gamble wants to send a huge quantity of toothpaste to a Family Dollar store because people are out of toothpaste and need toothpaste. And the question is, well, Procter & Gamble doesn't own their own trucks. Okay, they don't own those kinds of that infrastructure. So how are they going to get their toothpaste from the warehouse or from the factory to the store that needs it? Okay, where does that truck come from? Like, how do they get a truck to do this transportation? And so in the traditional trucking industry, so this is not what Convoy did. This is like before Convoy, like historically in the trucking industry, Procter & Gamble, or an employee at Procter & Gamble, will call up on the phone a person who works for a broker. So a broker is a specific type of person who it's their job to basically take calls from people who want to ship things and then figure out how to get them a truck when they need a truck. Okay, so they will call the broker, say, hey, I need to get this load of toothpaste on Tuesday. Can you find a truck for me? And the broker will say, yes, I can do that. And then what the broker will do is they will get on the phone and they will make a phone call to one of the truck drivers that they know. And they will say, hey, are you available on Tuesday to pick up this load in Milwaukee? And the truck driver might say, no, I'm in Houston, Texas today, so that's not going to work. I can't do that. And then the broker will make another call to a different truck driver and say, hey, can you pick up this load in Milwaukee on Tuesday? And that truck driver might say, oh, yeah, sorry, I've already got a load. I can't do that. And so they'll call a third truck driver and say, hey, can you pick up this load? And maybe that third truck driver says, yeah, I'm actually already kind of near there. That sounds great. I'll be there on Tuesday. And that's how the trucking industry works. Now, that's kind of incredible to me. When I first learned that this is how the trucking industry works, is like, in this day and age where so much is powered by the internet, how can we be running all of our infrastructure on phone calls, right? Brokers make so many phone calls because they have to call the first truck driver and say, hey, are you there? And then keep calling until they find someone who's able to take the load. And on the other side, the truck drivers are just waiting for these brokers to give them phone calls, right? And if they're in a particular place and they don't get enough phone calls, they're not going to have work to do their truck driving and make money. So this is a very inefficient system. So this is the problem that Convoy was trying to solve. We're going to do better, and you guys are going to work with me to kind of design this a little bit. We can do better. So the first thing that we can do better is, instead of this broker, calling up the broker and then calling up all the truck drivers, we are going to build a marketplace. Okay. So marketplace, again, in the real world is, there's a bunch of people who are trying to sell their stuff. Maybe it's vegetables, maybe it's their ceramics, whatever it is. And then people trying to buy those goods. So we're going to have something similar. Okay. We're going to have basically truck drivers buying shipments so that they can kind of do all this together. And in particular, we're going to have truck drivers bidding on shipments. So think of an auction, right? Truck drivers are trying to basically take a load for the least amount of money, right? Or the most amount of money, right? The truck drivers want to make the most for their load, but we're going to basically find the truck driver that will take it for the least amount of money. And then the second thing that we're going to solve today is one of the things that's so inefficient about this whole process is, if a truck driver takes one load at a time, say from Houston to Milwaukee, well, what are they going to do when they get to Milwaukee, right? They're going to have to wait and figure out how to find another load that goes from Milwaukee to, Portland, Oregon, something like that. And then from Portland, Oregon, what are they going to do? They're just going to have to wait again. So what we're going to try to do is we're going to try to bundle shipments together so that if you start in, Seattle, Washington, which is where I am, that you can get basically a whole bunch of shipments, one after the other at the start, so that you end up back where you started. So, I live in Seattle. I want loads that go from Seattle to somewhere else, but then come back to Seattle. And so we're going to offer those to the truck drivers all together so that, I have a guaranteed 3 shipments in a row that gets me back to where I started, back to home, which is a really nice thing for truck drivers. And we're going to do all this with computers. Okay, so instead of the phone calls, we're going to do this with computers instead. Okay, before we move on, any questions that anybody has about the general industry or the general problem that we're trying to solve? Feel free to unmute and ask your questions. No, great. Okay, feel free to unmute at any time. I really do appreciate questions and interaction. So first, we're going to start off with the marketplace. We're going to build a marketplace here. So my first question to you that I want you guys to kind of respond to me in the chat here is, what are the entities or the nouns in our shipping marketplace? Who or what are things we have to think about when we're talking about this marketplace for this, the trucking industry? Okay, so I hear someone responded, truck drivers. Yeah, drivers are definitely someone or, as an entity in this marketplace. Shipments, yeah, sure. We're trying to ship things from one place. So absolutely. Warehouses, yeah. So I see, someone said warehouses, we're starting, all of the shipments start at a warehouse and maybe go to a different warehouse. So absolutely. I see those drivers, shipments, places, warehouses, the people who sell the food. So that's I'm going to call those shippers. Oh, yeah, companies, shippers, the people who sell the food. Yeah, so I'm going to call those shippers, the people who want to get the stuff moving. And then I see bids. So bids, the truck drivers are going to make bids on things. Okay. Routes, receivers, time. These are all great things. I think we've covered the things that I wanted to cover for our little design sample here. So yeah, shippers who are trying to send things from point A to point B, drivers who are going to take the stuff from point A to point B, the actual idea of a shipment that goes from point A to point B at a certain time, the bid, which is what we're gonna basically the money component of this, and then the location, like a warehouse or a destination, where it's picked up and where it's dropped off. Okay, great. Thank you guys. That is perfect. So on the flip side, what about the actions that can be taken in this marketplace? So what are the verbs? Who performs those actions as well? So I want to know what are the verbs and who performs each of the verbs. Any thoughts on that? Okay, so I see something about finding truck drivers. So we need to like find a truck driver. Long driving hours, can you kind of, so like the actual driving that has to happen, right? So you have to drive the trucks, done by truck drivers. You have to pick up and drop off loads. Yep, the drivers are going to do that. Anything else? Company, the bidding on shipments, requesting shipments. Okay, yeah. So yeah, receiving loads performed by the companies. Yeah, so it's an interesting combination here. There's a combination of actions that are real world actions that really have to happen in real life. So like a driver has to pick up a load at a warehouse and has to drive across the country and then drop it off somewhere else. So there's like physical actions that have to happen. And then there's also virtual actions that are going to happen in our virtual marketplace, right? Like this bidding and, adding shipments and that kind of stuff. So I'm going to focus for the purposes of this, computer science software engineering presentation on the virtual side of things. So kind of as we talked about here, kind of the things that you might see here is you want to create a shipment in the first place. So, request that some driver be found to take your shipment from point A to point B. And that is done by the shipper or the company that's wanting to, ship this shipment. You might want to make a bid, and it's the driver who's going to make a bid on a particular shipment saying, I will carry this load for $400 or whatever it is. And then ultimately a shipper has to accept a bid. So if a driver says, I'll do this for $400, then a shipper has to say, okay, that's my best offer. I'm going to say, yes, please take my load for $400. Okay, so those are the three actions we're going to talk about right now. Cool. So putting these pieces together, I want to kind of demonstrate how I would go through this kind of software design process. Okay, so here we have all of the entities we talked about, the driver, the shipper, bids, shipments, and locations. And I'm going to draw a bunch of arrows between these things to kind of reflect how these things are related to each other and how those actions that we just found kind of tie them together. So the first kind of relationship here is that a driver makes a bid on a shipment, right? So the bid is, kind of related to a shipment. A shipment is then picked up at a particular location A and dropped off at a particular location B. Okay, so this is one way that you might represent the relationships between these different entities in our system here. And moving on to our verbs, we said that a shipper creates a shipment. So I would draw an arrow from shipper to shipment. A driver creates a bid, which is on a shipment. So that's another arrow. And then a shipper would accept a bid on a shipment. Okay, so any questions about this? This hopefully is something that seems pretty reasonable. We're just basically taking what we understand to be true and putting it down on paper in a way that's a little bit more formal. Okay. So this is our initial design diagram. So what we're putting together here is a design diagram. And the next thing that I want to do is basically, you might look at this and say, yeah, Melissa, sure, that makes sense. That's very intuitive. How does this relate to software engineering? How does this relate to computers at all, right? Like you don't need computers to do this. So I'm going to show you, I'm going to translate this chart bit by bit into something that makes sense on a computer. So the first thing is that the driver box, this concept of the driver is probably going to be using their phone to interact with our piece of software here, right? They're going to have some kind of app on their phone. They're in their truck. They're driving across the country. They're going to be interacting via some app on their phone. While the shipper is probably in an office somewhere, some Walmart office or Procter & Gamble office, working on their computer. And so they will be interacting with our application via a computer, via a website, something like that. Okay, so that's the first piece. So we're going to need some software for a phone, for a computer. And then the next thing is you don't just magically create a bid. You don't just magically create a shipment, right? All of this stuff that has to do with computers has to go through the internet, right? So a driver creates a bid, shippers accept bids and create shipments. Those kind of requests all go through the mystery that is the internet. I'm not going to go into what the internet is at this point, but somehow they go into the internet, you send a request, and then it comes out on the other end, where we're going to basically do that creation of shipments and bids and all that. Okay, so we've got the internet, we've got these requests. And the next change that I'm going to say is, well, okay, all of these things that have to do with bids, shipments, and locations, these are all occurring on our computer, or what we call a server. So in some data center or something like that, somewhere in the cloud, there is a computer, like a physical computer, that is running our code, and that is owned by our company, which we're calling Convoy here. Okay. And the next thing that we're going to add here is, remember we said we had actions, create bid, accept bid, and create shipment. We actually have to basically translate each of those into code, right? Into some logic that a computer can understand. And we're going to kind of separate those, kind of consider those separately. So I'm going to represent those as a little brain. There's some kind of little logic that's happening for each of those actions. And then those are then interacting with the bids, the shipments, the locations. And then last but not least, instead of kind of visualizing bids, shipments, and locations in this manner with the interconnectedness, in reality, bids, shipments, and locations are going to be stored in something called a database, which if you're familiar with database is great. If not, think of it like a file folder or like a filing cabinet, right? So in the bids drawer, we've got all of the bids for all of the shipments that we have. And then we have a shipments drawer and a locations drawer. And each of those locations and shipments is all filed in one of the drawers in this database. And so when you create a bid, you're essentially putting a new file into the bid drawer of our database file cabinet. Okay. So that's essentially what this is the design for an application like this. This is how the internet works. This is how Convoy really worked, okay? And so the question is, well, what is the code that we, as the people designing this application, are actually going to have to write? Well, we're actually going to have to write the code for the stuff on the driver's phone app and on the website. And then that logic, the kind of what we do when we create a bid, accept a bid, or create a shipment. So those are pieces of code that we'll write. And for those of you who have programmed before, you can think of create bid, accept bid, and create shipment as essentially functions or methods. So actual pieces of code that are individual that we have to write one by one. Okay. So it turns out that this marketplace that we just built here with creating bids, accepting bids, shipments, whatever, is similar to a lot of other different marketplace applications. Does anyone have any other examples of online marketplaces that you think are probably similar? I see Uber, yeah. Amazon, yeah, you're buying things and you can sell things on Amazon as well. eBay, yeah, any of the auction sites, absolutely. Yeah, I'm sure there are a lot. DoorDash, okay, yeah, any of these things where you're trying to buy things online. Yeah. So I think you got a few of the ones that I had: eBay, Etsy, Amazon, and Uber and Lyft. There's many more. There's lots of different online marketplace applications. And what I want to emphasize is they're all pretty similar, right? So the cool thing is you think about one of these problems, like, oh, I want to build a marketplace for truck driving. This design is very applicable to a lot of other different use cases as well. So this is the software design process, which is pretty cool. But there's another aspect that I wanted to talk about, which is bundling shipments together. Okay, so remember, here's what I meant when I said bundle. I am a driver. I want to find work. Okay, I need to find shipments so that I can drive them across the country so I get paid for it. okay? If I'm starting in a particular location, say Lexington, and I want to end at the same location because I live here, for example, and I want 2 to 3 shipments in a row that will guarantee that I end back where I started, okay? So for example, I want to go from point A to point B to point C to point A, or point A to point B and back to point A again, okay? And that's great because then it means I have continuous work and I'm guaranteed to come back to where I started, okay? So we want to do this to make it easier for drivers to find good work. But it turns out in a really successful marketplace, you're going to have so many shipments, okay? So let's say there's a company that wants to go from Seattle to Los Angeles on 11/16 with delivery on 11/19, from Nashville to St. Louis, from Houston to Chicago, there's so many shipments. So how are we going to find these bundles? Like, how do we represent this? How do we think about this in order to find these bundles? Okay, so what we really want is, like, from this huge list of shipments, we want to find these 3 shipments that we can bundle together. So one that goes from Lexington to Boston, from the 16th to the 18th, and then on the 18th, you pick up another load in Boston and go to Detroit for the next day, and then pick up in Detroit one day following and deliver back in Lexington on the 21st. Okay, and so the driver says, yes, I am going to take the whole bundle, not just one of those loads, which is very convenient for them. Okay, so what we want to do is we want to take this big list and we want to turn it into kind of sets of bundles like this. Okay, great. Cool. So, I saw, we'll follow up with this question at the very end, and we'll talk more about how the shipping industry works. Okay, so one thing that might help us in solving this problem is you can think about shipping in the United States as based on routes. I think someone mentioned entities of routes somewhere up in the chat, which is absolutely right. So you can visualize the whole country as consisting of these routes between the nodes of essentially locations or warehouses, cities that are commonly used to basically pick up or deliver goods, okay? So we visualize our kind of whole network here as a series of nodes and then the roads between them, okay? Makes sense? Seems pretty common. It's like a typical roadmap in the United States. So I'm going to introduce the concept of a graph. So I think a couple of the other presenters mentioned the term graph before, but we didn't really talk about what a graph means. But I want to be a little bit more precise about it because I think this is a very key point in software engineering and in computer science and is really interesting to talk about, okay? So when I say graph, you might think of this kind of graph, right? This is a typical XY plane with, lines and, kind of that kind of graph. That is not what I'm talking about here. When we say graph, we're talking about something like this with different little nodes and edges between them, okay? So in programming or in computer science, the official definition of a graph is a representation of items. So those are the nodes here and the relationships between them. So in this example, there's a relationship between A and B. There's a relationship between A and C, between C and D, etc. Okay, so that's a graph in our terminology. Can anyone give me some examples of other types of graphs in real life that you can think of, where we have items and then a bunch of relationships between those items? Class schedules? Yeah, sure. So like prerequisites between different classes. You have all the classes, but you have to take class A before class B. Yeah, sure. The stock market, you have stocks and relationships between those stocks, like, something that can cause one stock to go up or down causes another stock to go up or down. Maybe that makes sense. Venn diagrams is a different type of representation. I wouldn't say it's necessarily a graph, but it is a representation of items and the relationships between them. Wikipedia links, yeah. So if Wikipedia pages are each of these items, and a link between one Wikipedia page and another Wikipedia page is like a link between them. Yeah, so that's like links in Wikipedia or in the internet, right? Any kind of hyperlink on any web page. Family trees, yeah. So if people are the items, the relationships between them would be like parent-child relationships or evolutionary trees, all of those kinds of things. Yeah, so all of these are great examples. Some more examples are friendships. So if you have people and then friend relationships between those people, family trees, hyperlinks, airline routes, very similar to the shipping routes that we're talking about here, roadmaps and shipping lanes, all of these good things. So these are all graphs as we define them. Okay. So in our shipping graph, what are our items? What is an item in our shipping graph of the United States here? Anybody? We've got route lines, we've got time and dates. Yeah, so, but then we say the items are the places, the relationship to the start and end points. So going back to kind of our graph here, yes, so, what are the little dots, right? So we've got lines connecting the dots. What are the dots? The dots are locations, basically the pickup and drop off points, the cities that we care about in this conversation, okay? So those are our items. The items are the points, right? The points. And then what are the relationships representing in our graph here? Basically the lines between the points. What do those represent? Distance, yeah. So like, some kind of road that exists that's some distance between the starting and the ending point. Okay, so not the vertices. The vertices are the locations, right? The starting and ending. The lines represent like roads or like actual routes between the two places. Does that make sense? So our items are the locations where the shipments are picked up and dropped off. So like a city. And the relationships between the items says basically there is a shipment from location A to location B. So if they're from location A to location B, there has a connection there that says that there is a location or there is a shipment that goes from A to B. Okay. So that's basically the shipment routes, right? But we're going to say if there is a shipment that goes from A to B, that means that there's a relationship between A and B. Does that make sense? Okay, so if we think about it this way, our graph for the example shipping list that I had before might look something like this. Okay, so we've got all of our different cities and we've got arrows between them. So you might see here that if we've got an arrow from Seattle here to Los Angeles down here, that means there's a shipment that starts in Seattle and goes to Los Angeles, right? Similarly, over here, you can see that there is no arrow that goes from Boston to New York, which means that there is no shipment currently that anybody's trying to send that goes between Boston and New York. So that's how to read this graph. Okay. Questions about that? Because we're going to use this graph now. Okay, cool. So again, to reiterate, what we are trying to find in order to find these bundles is if we start at location A, I want to find what we call a path. So kind of connected shipments that connect location to location. We want a path of 2 to 3 shipments that ends back at location A. Okay, so I want it to be a loop that ends back where we started. Okay. So here's an example graph, right? So we have, what is this, 7 different cities. And I want to start and end in Lexington. And an arrow from one place to another means there's a shipment that starts from one place and goes to another. So for example, here, if we start in Lexington, there's an arrow that goes from Lexington to Chicago, which means there is a shipment that goes from Lexington to Chicago. Makes sense? So I want you to take a minute or two and try to find as many bundles of 2 to 3 shipments as you can in this graph where we start and end at Lexington. Okay, so take a minute, think about which 2 or 3 cities are involved in this bundle. And there is more than one, so you can keep trying to find them. Okay, so I see someone who was saying one that had 1, 2, 3, 4, 5, 6 cities. So remember, we're trying to keep only 2 to 3 involved shipments. Okay, so I only want like a triangle or like a just out and back in this case because we're keeping it short. Yeah, so I see some good examples here. So someone said Lexington to Los Angeles. So you follow this arrow here and then back to Lexington. Yeah, that would work. I see a Boston to Lexington, same thing. So you go to Boston from Lexington and then come back. Yeah, that would also be correct. How about Lexington to New Orleans to Boston, and then back to Lexington? Yeah, I think that would work. And then I think the last one here is what? Lexington to, I think it's Chicago, right? So follow it to Chicago. Chicago can go to Los Angeles, and then Los Angeles can go back to Lexington. That makes sense? So I think all of the ones that I could find are with only 2 to 3 stops, right? Only 2 to 3 are these ones that we pointed out here. Okay. So that's great. We did this manually. But I want you to think for a second, how did you figure it out? Like when you were doing it in your head, what was your process to figure out how to find these bundles? Now, this is a little bit more complicated, so I'll give you a second to type out some thoughts. But I am curious, can you describe in words what your brain did to find these bundles? Cool. So I see some interesting different approaches, right? So some people are looking at starting in Lexington and then looking at all the arrows that go out of Lexington and then try to find things that come back or, keep going. Some people are looking at ones that go into Lexington and then going backwards. So that works too. So something like this, right? You're looking at the arrows and then following them either forward or backwards to try to find these loops, right? So these are all very reasonable approaches. There's different ways to do this, kind of efficiently. I'm going to describe one of these approaches, which is the more forward approach, I would say, which we call an algorithm. So these are just the instructions for how to build a bundle, and we call this an algorithm. Okay, so the algorithm that I'm going to propose is that we start at location A, and then we look at every shipment that leaves that location and goes to a different location. Okay, so we're going to start in Lexington, look at all the outgoing arrows. And then when we kind of look at one of those options, we look at all the ones that leave that location. And we say, if we go back to the one we started at, then we found a bundle, right? That's an out and back. Great. A more complicated one is, okay, it's not an out and back, it's an out and it goes to a third place, location C. Well, we have to do it again at location C. We have to go back to location C and see if there's anything that comes back to A. Okay, so that's a lot of words. Let's kind of walk through it. Again, this is how your brain probably did it, but we're just being very explicit about the rules. Okay, so let's say, we start going up. We start with Lexington to Chicago. So we say, okay, Lexington to Chicago. Is there an outgoing edge that comes back to Lexington? No. So we're going to look at all of the different outgoing shipments from Chicago. Okay, turns out there's just one. So the outgoing from Chicago to Los Angeles. is, kind of what we're going to follow. So now we're in Los Angeles, and then we're going to look at all the arrows that go out from Los Angeles. So the first one goes to Seattle. Is this Lexington? Basically, are we back where we started? And the answer is no, we're not back where we started. So that's no good. So we're going to try the next one. So we're going to try, oh, well, Los Angeles to Lexington. Yes, that is where we started. So now we've kind of satisfied, we've found a proper bundle. And you would keep doing this for every single kind of arrow that comes out of Lexington. Does that make sense? So we just repeat this for all the arrows. And it turns out that what we just described is a very classic algorithm in a graph that is called a depth-first search. So if you've ever done a maze, right, like a little maze activity, you have probably done a depth-first search, right? So you try to solve the maze, and if you get to a dead end, then you backtrack and try a different approach. And eventually, if you keep doing this enough times, you are going to find the answer. You're going to find the exit of the maze. Okay? And this is exactly the same thing that you are doing when you're looking through your graph and trying to find these cycles. Does anybody else have any other examples of depth-first search or things where you're trying to solve this type of problem and you do a search in this way? Think of anything? A word search? Okay, yeah. So you're doing like little word puzzles. Anyone else? Wordle, yeah. It's, something like Wordle might be similar. Yeah, it turns out that there's a lot of puzzle solvers that are kind of similar. But there's also things like we talked about how, Wikipedia is a graph. Has anyone done the like clicking on Wikipedia links to find interesting things where you keep like starting at one place and try to find a way to get to a different place, in Wikipedia, like Wikipedia finding? That's also probably you're doing a depth-first search there as well. So that kind of thing is very common. So kind of, I was like, okay, here you go. Here's how you solve these bundles. It turns out it's actually a little bit more complicated in real life. Anybody have a guess as to why it's a lot more complicated than just what we did just now to find these bundles? What did we miss? What did we not think about? Things can change on the fly. Okay, so like things are slow or like, you have traffic. And so what happens then? Truck driver gets sick. Yeah, absolutely. We didn't take into account how long these different routes might take, right? The distance between the points and like when you pick up, right? So we had some notion of a shipment starts from point A to point B at a particular time on a particular date. And so you need to make sure that those kind of align together, right? So you have to make sure that if you have shipment X and Y in a bundle, you have to make sure shipment X ends before shipment Y begins. Otherwise, you can't have a driver in two places at once, right? And so this is something we call a constraint. It basically restricts the set of solutions that we can provide. I'm not going to go into kind of the details of how we might implement that, but the idea is, you take this and it gets slightly more complicated by adding each of these things. Okay. So congratulations, you have learned about graphs. You've learned your first algorithm on the graph. This topic, graphs and algorithms, is the subject of my 300 level computer science topic that I was teaching to Adi. Computer scientists and software engineers, we use graphs to solve problems all the time. It turns out graphs are a super common concept. And if you continue in computer science, you'll learn so much more about how powerful this concept is and how to use them to solve problems that even don't seem like they have to do with graphs, but actually really can be solved with a graph algorithm. Okay. So now that you've learned a little bit about graphs, I'm just curious, are there any other types of graphs that you've seen in your life or in real life that you think kind of a graph would represent them well? Yeah. Career paths. Yeah, sure. If else statements in Java. Yeah, so different ways through code. There's so many different cases where graphs can be applied. So all of these are true. Okay, so what we just did, we figured out who is going to use our app. We figured out how they're going to interact with our app. We came up with a way to represent shipments going across the country. And then we devised an algorithm to create bundles of shipments together. What didn't we do? So one thing you may have noticed here is we did not write any code. I did not refer to code in any respect, okay? And that's actually because software engineering is about so much more than just code, okay? We might emphasize, oh, programming and Java and Python. Like we talk about that a lot. Software engineering and computer science is not just about code. It's about design. It's about engineering. It's about building things. Okay, so it's not just the hacker who is hacking away on their computer and writing code all the time. It's about building things. It's about being diligent and understanding what we're trying to build. Because if someone tried to build an apartment building, for example, and didn't have a plan, they would not be able to build that apartment building successfully, right? It would be willy-nilly, it would fall down. Software engineering is the same way. You have to have a plan. And ultimately, it's just like those jigsaw puzzles that I loved as a child, except a lot bigger and a lot more complicated. So that's why I really enjoy what I do. You might say, is that actually really software engineering? What we just did, these little boxes with arrows and a couple graphs, is that really software engineering? And I want to tell you, yes, this is really software engineering. So when I am solving a problem, what I always do is figure out who is going to be using my code, figure out how they will be interacting with it. I make those box and arrow diagrams all the time. And then I use or invent algorithms to solve the problems that I'm trying to accomplish, okay? And just to reiterate, I spend a third of my time doing design, so kind of what we did in this lecture. I spend only 1/6 of my time actually writing code, okay? So I do twice as much design as I do writing code. And then the last half of my time is spent testing, which is a whole nother topic that we're not going to go into, but basically making sure that my design and code work like that I expect them to, okay? The real takeaway here is that design is like twice as much as the actual code of what I do on a day-to-day basis, okay? I want to make sure that you guys have time for questions. One example of what I have built in the past is if you've ever watched a live video on Facebook, there's like live comments and reactions, people commenting and reacting in real time. That's one of the projects that I've worked on and tried to build. It's really hard because you have to make it fast, and because on really popular videos, you can have up to 1 trillion messages per minute going through the system, which is a really big scale. And so trying to build that with really low latency is quite difficult, but involved a lot of arrow diagrams and graphs and that kind of thing. So that's all I have. I think I'm over time, but that's okay. I had one question that I saw way back up here that I wanted to address. Someone had asked, was this problem the problem that Convoy was solving based on the premise that companies don't typically partner with shipping companies to move product? The answer is that in the vast majority of cases, the trucking industry is made up of small businesses, okay? So relatively small, like businesses, mom and pop type shops that have, a couple trucks, 5 trucks, 10 trucks, but not more than that. And there are companies that have dedicated truck fleets. So for example, Walmart might have their Walmart trucks and they ship all of their stuff via Walmart. But most companies do not have their own truck fleets, and so they have to work with smaller truck businesses in order to do this kind of thing. So that's a little bit about how the trucking company works. Anyone else have any questions? Feel free to unmute if you have.
Hi, Melissa.
Hi.
I actually had a question, like considering the current job market.
Yeah.
I'm currently a first year CS major, and I'm in the space of looking for something to kind of enhance my path in the next few months.
Yeah.
what's your opinion on like current opportunities for first year majors in the software engineering space, such as internships or
Yeah.
working opportunities while in school?
Yeah, so you're right. The industry has changed quite a bit since I was here, I'm going to stop sharing because I think better to talk to you guys without it. How do I stop sharing? Um, the industry is a lot different than when I joined, and it's harder for new grads right now. That being said, I think internship opportunities are still widely available in a lot of companies. So I do highly recommend that even if it's a smaller company, putting out those feelers and trying to get an internship as soon as possible is definitely awesome and will, make your resume stronger. So in my experience, internships are still happening. The actual conversion from internships to full-time is trickier given that things have slowed down a little bit. So I would still try to find internships as much as you can. That is the number one thing that companies are looking for. Other things you could do, getting involved in research, like I think some of these other professors have talked about, I do think is a good thing, even if you're ultimately not interested in research, even if you're interested in software, because you're going to get some coding practice and you're going to get to, like have some of that real world experience that will then look good or translate into a career in software engineering. And then ultimately, this is a field where you can just do it, right? You can just come up with a problem and write some code to try to solve it. And so if you have, you're not able to get an internship or anything like this, find a problem and try to solve it yourself. And those kinds of personal projects you can post publicly, open source, on like GitHub or things like this. And this is one way to gain experience and make your resume look good, even without an official internship. So that's my other recommendation.
Thank you.
Anyone else?
I'll also say I think we have just sort of all the professors that have spoken that are back. So we can honestly just kind of for the rest of the time open it up to just like all the professors in general and just sort of see like if anyone has any questions at all, go ahead and ask. So I think we did get one through the chat of do you know any good books on software engineering?
Feel like I I can get back to you in terms of specific books. A lot of it is practice, right? I think software engineering in particular it's engineering is a complicated word that involves a lot of different skills. And so, for example, I teach a separate course that is just on software engineering, and we talk a lot not just about like this design process, but also testing and communication and like all kinds of things that are not directly related. So one book is a little bit tricky. Let me get back to you.
What are your personal like favorite resources for, those that are like from my end as more beginner entry level into like the world of software engineering and computer science? What are your favorite resources to like dive deeper?
So, I think one of the things, so I don't want to go too deep, but some of the favorite resources that I have on the software engineering side in particular are a lot of the resources on prepping for interviews. So actually, a lot of the resources on prepping for like computer design interviews, you have to be a little careful because some of them are very detailed, but a lot of them have like great kind of starting resources. So like, oh, I want to design Uber or I want to design Twitter. Like, how would you even get started with that? I think some of those interview resources that walk you through how to do an interview on that is a good place to start in terms of like thinking about how you would design these types of larger applications. So that's one place that I would suggest.
I actually do have a question, and I guess we could, it's sort of directed at whoever wants to answer, but I'm just kind of curious generally, how was computer science sort of first introduced to you? Just to get sort of a little bit, I know you guys kind of all went in a little bit into your backgrounds, but just like generally, how do you remember computer science being interested or introduced to you, and like why do you think you stuck with it?
Well, I guess I could maybe start off a little bit. So I think, if we go way back, I think the time where I first started to put two and two together, that like computers were nifty and I could maybe do something with them, was my dad had an old work laptop from the late 80s. It was about this thick, it was sizable. The batteries had lead in them. It was a very heavy thing, and it played a few simple games on it. And I played those games a lot. And at some point, Dad showed me that you could program things in a language called QBasic. And he didn't really know too much about it, but basically knew enough to show me how to do things with like conditionals and print statements. And I thought it was interesting that I could kind of create that way. Um, I sort of focused a little bit more on the hardware side of like robotics and stuff later on, but like, Lego Mindstorms was fun, even if the programming I was doing was mostly graphical. Um, I think in terms of software engineering, I really only started getting into that pretty late when my PhD research founded a startup, and suddenly we had to start thinking about like writing code that was going to run in more than one place. So for me, it was a little bit later in the timeline.
My background here is I didn't start. I took a computer science. I took a HTML class in high school, and it was probably my worst class in high school. Like I hated it. It was just so boring. The teacher was basically said, "Go do your stuff," and then ignored us and didn't teach us anything. It was really not fun. And so I took a computer science class, my first computer science class, my sophomore year in college. And I had never really considered it before. It was a thing that my brother did, right? It was his thing. It wasn't my thing. But that class was so fun, just the problem solving aspect of it. Then I went and talked to the professor, and he's like, "It's not too late. You can do the whole major in 2 years. Like you could do this." And so, that's when I decided that like this is really fun. I just want to do this my whole career. Um, yeah.
Yeah, I guess for me, I didn't do any computer science in high school, and I first got exposed to just programming and kind of an intro level uh, computer science course in undergrad, and I guess on the theoretical side of things, I only sort of knew about this area with when I first took an intro to algorithms class, and then started doing some research in the summer of my second year in college. So yeah, for me, like research was the thing that really like opened my eyes to uh, kind of this whole field. So I know Melissa mentioned try to find opportunities to do research. Yeah, I highly recommend that as a way of like broadening your experience with computer science in undergrad.
Absolutely. That's awesome. Thank you. And then obviously we are still do have like a little bit of time. I think we did finish like a little bit ahead of schedule. But yeah, I mean, just in general, as kind of final wrap ups, anyone can still ask questions, by the way. But I did want to say just thank you to all of you guys for coming out. Um, I had a great time listening to all the speeches and everything. Ricardo, I'll let you go ahead and ask your question. I'll sort of do this afterwards then.
All right.
So it's kind of a somewhat general question for all three of you. Obviously, the three of you are from more prominent universities when it comes to the computer science program in general. Do you guys have any advice or anything that you feel like sets students apart in terms of undergraduates applying for master's programs or like anything that would, yeah, just generally make them stand out from the rest in terms of applications to graduate programs?
So I guess like one quick thought might be uh yeah, so definitely try to enlist the help of like mentors early on in your college career to try to establish relationships, for instance, with either faculty or folks in industry that can write compelling letters of recommendation, because that's you know, a big part of the process. I think the other thing to keep in mind is certainly like when crafting the statement of purpose in your graduate materials, try to be, you know, as thoughtful as possible in terms of, you know, not just listing out, okay, these are like some big, like super vague, like general areas that you want to pursue, or, you know, study more in depth, but articulate like, you know, here are some actual concrete directions that you've thought about. They might not end up being the topics that you will study in your graduate program, but it's always helpful when you know, potential you know, graduate advisors see that the student, you know, has already kind of entered this research mindset and can hit the ground running. Yeah, so those are some small things.
Are you talking, Ricardo, are you talking about master's programs or PhD programs in particular? Or both?
Well, PhD would of course be the ideal end goal, but
Okay.
I guess I was just more so referring to master's programs as a start.
Okay. Yeah, because one of the things that I've noticed, so for example, the University of Washington does not have a master's program. They have the PhD program, they have their fifth-year master's program if you went to undergrad there, and they have a professional master's program, but they don't have a regular like master's degree program. I don't know if this is a common thing across universities that mostly they want you to do PhDs. Master's programs that are more professional master's programs or that kind of thing are an option as well. However, if you're not trying to do a PhD, if you're just trying to do a master's, I would question why. Why are you excited to do a master's and not a PhD? If you want to do a PhD, that's great. Master's doesn't get you a whole lot on top of just having a bachelor's in computer science, in my experience, right? The amount of experience that you can get in 1 year in industry is so incredible that like it really is like just as good, if not better, than your master's program. So, you know, like not saying don't do it. I did a master's degree, but I did it because specifically they gave me the opportunity to teach and there was some specific research that I wanted to do. So, you know, kind of as Sitan mentioned, you know, like think about your purpose, right? Why are you interested in this? And I think that, you know, is where you can really stand out and what can make your application special.
I think the only thing I'll add, and primarily I work with undergrads, though I do have master's and PhD students who take my classes. I would say this is more sort of a general thing that I've noticed about like what do people look for. There are so many applications that folks are going to be flipping through. Doesn't matter what you're applying for. It's a stack like this big, and somehow you've got to stand out. Like I won't pretend like application processes are far from perfect, and you have to make yourself stand out so that you don't get unlucky and like when your application bubbles to the top is when whoever is looking at it gets to a good part of their Netflix show that they've got in the background. It's messy, but one strategy for standing out is to make sure that you are telling a cohesive story. I would say focus on more than just grades, things like that, because, you know, plenty of folks have straight A's. It tells you nothing about them aside from, you know, they played the game well. Um, think about how to craft something so that someone is going to want to say, hey, guess who I read about today? Guess what they did? Focus on things that you've done, things that you're excited to do. And if you kind of don't know what those things are yet, try to start making some time in your schedule for them, even if they're personal projects or like things that you're volunteering to help out with, open source projects, etc. Just make sure that you are telling a story that isn't just the numbers.
All right, thank you very much.
I see we've got a question in the chat that's kind of similar to that. I can say at the very least at CMU, and I would expect probably elsewhere. I think the biggest thing that folks are kind of looking for in a broad sense is that you have taken advantage of the resources that you have available to you to the fullest extent possible. That doesn't necessarily mean you have joined every single club, but just you have made use of, the context that you've been in high school, essentially. That could be focusing on one thing, or it could be diversifying your interests. But I would say, especially for those who are kind of like worrying, like, well, what if somebody else goes to a course that, or goes to a school that offers all of these courses that my high school doesn't have? Do I stand a chance against them? And I can say pretty confidently, at least at CMU, yes, you do, because your application is being viewed side by side with what you have access to in your environment. So just yeah, like explore the space that you are given. And I think that's what CMU is looking for.
The ability to demonstrate curiosity and to demonstrate excitement about something, whether that something is directly computer science or not, is really valuable.
All right, I have one more question. So I just asked earlier about master's and PhD program applications. But my ideal path would be to get into a PhD program and end up doing research. Is there anything that any of you have experienced in terms of research that you wish you knew beforehand, or like major mistakes you made that obviously everybody learns from mistakes, but something that you would recommend people look out for in terms of PhD programs in general and getting into further research?
I've certainly got one, but does anyone else want to lead off? Well, I will I'll be upfront with you. I really wanted to get a PhD. It took me 3 tries. I had to apply 3 times before I specifically, granted, I was aiming specifically for the Robotics Institute at CMU. And the first 2 times I got turned down. The first time they did let me into a master's program, so I went and did that. It was really frustrating at first to get turned down a couple times. But I also understand in retrospect why that happened. And the things that I wish I knew before were this. There are certain PhD programs where research is like, seeing that you have done some prior research is not just important, it's essential. They're going to want to see that you have done research and that you have published something, so that they know that, like, you can do the science, but you can also write something that's going to contribute to, a body of knowledge. And part of my mistake was I had 2 research projects. I spent 2 summers doing research. that basically boiled down to we built some really cool robots and we spent so much time building the robots that we never wrote up anything about them. At least we never wrote up anything that we shared with the world. So one might ask, what was the impact of doing that if we didn't share that knowledge? And the second thing, and don't get me wrong, this is not saying you should not work on research projects for, I don't know, like a company that makes you sign an NDA or, the Office of Naval Research was my case. But I spent 2 years on a project, a robotics project with the Office of Naval Research. But I had to sign a 5-year NDA that was very tight. I couldn't really say what I was working on at the time. And so when it came time to apply for PhD programs, I basically had to be like, yes, I have been working on a tremendously awesome robotics project for the last 2 years, but I can't tell you what it is. So just trust me that it's cool. And that wasn't really substantial enough, and we couldn't publish anything about it. Again, it's not saying don't do that, but just know that some PhD programs are really going to be looking for that publication record. I think that was my experience, at least.
Maybe yeah, so one suggestion is also when you're looking into these schools, if you have a sense for the kind of work or the PIs that you'd be most interested in, definitely like during application season, before you send out the application, also just double check that the PIs in question are actually looking for students that cycle. In certain cases, if their group is totally full and they're maxed out for for that academic year, no matter how good you are, they might just say, look, I'm not recruiting students this cycle. And being aware of, especially for your, first or second choice schools, like being aware who's actually hiring can save you a lot of like wasted time. That's like one small thing. And then also when you're trying to like finalize decisions, I would also highly suggest not just speaking to the faculty themselves, but also to their research groups, and just like students are very honest with how things are going in the lab. So just getting a sense for what the environment is like. You can get it straight from the source by asking like students and postdocs for that.
All right. Thank you, everybody.
All right. I mean, it looks like it's about time for things to sort of wrap up, but I do want to say thank you again to everyone for coming out, especially all of our professors who spoke. I had a great time listening to everything, and I hope everyone did as well. As a quick follow-up, I'm going to throw in a little feedback form in the chat, as well as an email that you guys can reach out to me with if you have questions about anything, or if you'd like to be connected with anyone. So I'll go ahead and send that. But if you could, please fill out the feedback form. It just sort of helps me know how like this event was for you and if you'd like to see like similar sort of things. But yeah, I really appreciate everyone coming out. And yeah, I just want to say I hope everyone had a great time. I was recording each of the speeches, so they should be up on the YouTube channel. And if you would like to stay like sort of keep your eyes on the email list. I'm planning out on sort of sending a compiled document of like resources and other things to look into for pursuing computer science and learning about a lot of these things on your own. And a lot of those will include the resources that the professors here talked about today. So yeah, just keep your eye out on your email list for that.